Welcome to today's paper reading. Today's paper is titled, Logits of API-protected LLMs Leak Proprietary Information. This paper, authored by Matthew Finlayson, Xiang and colleagues from the University of Southern California, discusses the leakage of proprietary information from API-protected large language models, LLMs. The work is currently under review. The commercialization of large language models, LLMs, has resulted in the common practice of restricting access to proprietary models via a limited API. This work demonstrates that, under a conservative assumption about the model architecture, it is possible to learn a significant amount of non-public information about an API-protected LLM from a small number of API queries, costing less than $1,000 for models like OpenAI's GPT 3.5 Turbo. The key observation is that most modern LLMs suffer from a softmax bottleneck, which restricts the model outputs to a linear subspace of the full output space. This bottleneck is exploited to unlock several capabilities, efficiently discovering the LLM's hidden size, obtaining full vocabulary outputs at a low cost, detecting and disambiguating different model updates, identifying the source LLM from a single output, and even estimating the output layer parameters. Empirical investigations show the effectiveness of these methods, such as estimating the embedding size of OpenAI's GPT 3.5 Turbo to be about 4096. The work also discusses potential defenses against such attacks and how these capabilities can be viewed as a feature for greater transparency and accountability. The introduction of this paper highlights a critical issue with the current setup of large language models, LLMs, being made available only via APIs. LLM providers may mistakenly believe that their model architecture information is private and that certain attacks are infeasible, fostering a false sense of security. However, the paper demonstrates that many LLM APIs reveal more about their underlying models than previously thought. The authors introduce a method to extract detailed information about LLM parameterization using common API configurations. This method allows LLM clients to track model changes, recover hidden prompts, and obtain full vocabulary outputs, thereby holding providers accountable. The approach also enables LLM providers to establish unique identities for their models, fostering trust with users and improving accountability. The method exploits the low-rank output layer common in most LLM architectures, observing that this layer's outputs are constrained to a low-dimensional subspace. This restricted output space, termed the LLM's image, can be obtained by collecting a small number of LLM outputs, facilitated by novel algorithms developed in the paper. Table 1 provides an overview of the applications proposed in the paper that exploit the low-dimensional subspace, or image, of LLMs. These applications include efficiently extracting full LLM outputs, finding the embedding size of an LLM and guessing its parameter count, identifying which LLM produced a given output, detecting when and what type of LLM updates occur, finding tokenization bugs, approximately reconstructing the LLM's softmax matrix, cheaply and accurately reconstructing hidden prompts, and implementing basis-aware decoding algorithms. The table categorizes these applications by section in the paper, highlighting the broad range of capabilities enabled by understanding the LLM's image. Figure 1 illustrates how large language model, LLM, outputs are confined to a low-dimensional subspace of the full output space. This characteristic allows for the analysis of API-protected LLMs by examining their outputs. The figure demonstrates the linear transformation of a toy LLM's low-dimensional embeddings in RD, represented as a 1D space, into Logits in RD, a 3D space, through the softmax matrix W. The resulting outputs reside within a D=1 dimensional subspace of the output space. The softmax function maintains this low dimensionality when converting logits into probability distributions on increment V. This low-dimensional subspace, termed the image of the model, can be used to obtain a basis for an API-protected LLM by collecting D of its outputs. The model's image can uncover non-public details, such as the LLM's embedding size, and can also serve accountability purposes, like verifying which LLM an API is utilizing. The architecture of a typical LLM involves a transformer with an embedding size D, which outputs a low-dimensional contextualized embedding H. This embedding is then projected onto RV through a linear map defined by the LLM's softmax matrix W, resulting in the Logits. Since W is in RV times D, its rank is at most D, meaning the Logits will always lie on a D-dimensional subspace of RV. The final output of the LLM, the next token distribution P, is a valid probability distribution over V items, forming the V-simplex increment V. This space is isomorphic to a V-1 dimensional vector subspace of RV, specifically the hyperplane UV perpendicular to the all-ones vector 1V. The softmax function serves as an isomorphism between UV and increment V, with its inverse being the center log ratio transform, CLR. Figure 2 illustrates the architecture of a typical language model. The input is first processed by a neural network, typically a transformer, which converts it into a low-dimensional embedding H. This embedding is then multiplied by the softmax matrix W, which linearly projects it from the D-dimensional space RD to the V-dimensional space RV, resulting in the Logit vector. Finally, the softmax function is applied to the Logit vector to produce a valid probability distribution P over the next token candidates. Figure 3 illustrates the mapping of points in the Logit space RV to the simplex increment V via the softmax function. It highlights that points on the same diagonal in RV are mapped to the same probability distribution in increment V. The figure also shows the CLR transform, which returns probability distributions to points in the subspace UV of the Logit space. This demonstrates the isomorphism between UV and increment V, where the softmax function and CLR transform are inverses of each other. Table 2 provides a summary of the proposed algorithms, detailing the number of API calls required per output and the cost of acquiring the model image. The estimates are based on a GPT 3.5 Turbo-like API LLM with specific parameters. The table highlights the complexity, API calls per output, and image price for each algorithm, including the logprob free, with logprobs, numerically stable, stochastically robust, and LLM image algorithms. Notably, the OOD algorithm cannot be used to obtain the LLM image as it requires the LLM image as a pre-processing step. The paper presents methods to recover full vocabulary outputs from API-protected large language models, LLMs. Initially, an algorithm requiring O, V log 1/epsilon, API calls is discussed to obtain full outputs with precision epsilon. An improvement is then introduced, theoretically reducing the number of API calls to V/K for APIs returning the log probability of the top K tokens. However, this improved algorithm faces numerical instability, leading to a numerically stable version that requires V/K-1 API calls. For stochastic APIs, an algorithm is proposed to collect full outputs in less than NV/K-2 API calls on average. Finally, a pre-processing step is added to reduce the number of API calls to OD, making the process up to 100 times faster and cheaper. To infer the embedding size of an API-protected language model, we collect the linearly independent outputs from the model. These outputs form a basis for the model's image, meaning all subsequent outputs are linear combinations of the first D outputs. We use the property that a matrix with D linearly independent columns will have D non-zero singular values. By plotting the singular values of the output matrix, we observe a drop in magnitude at index D, indicating the embedding size. We validate this method by collecting next token distributions from several open-source LLMs from the Pythia family, finding that the singular values drop dramatically at the index corresponding to the embedding size. This method is also effective against API-protected LLMs like GPT 3.5 Turbo, where we predict the embedding size based on the drop in singular values. Figure 4 illustrates the singular values of outputs from various language learning models, LLMs, with both known and unknown embedding sizes. For each model with a known embedding size, there is a noticeable drop in the magnitude of singular values precisely at the index corresponding to the embedding size, denoted as D. This characteristic drop helps in identifying the embedding size of models, including those with unknown sizes like GPT 3.5 Turbo. The figure effectively demonstrates how this method can be utilized to infer the embedding size of LLMs based on the behavior of their singular values. The image of different LLMs, including different checkpoints from the same LLM, are largely disjoint. This means that the logit output from a specific checkpoint of a model, such as Pythia 70M, lies uniquely within the image of that checkpoint and not in the images of preceding or following checkpoints. This sensitivity to small parameter changes suggests that the image of an LLM can act as a unique identifier. This has practical applications in LLM accountability, where providers can verify the authenticity of models. Additionally, this sensitivity can be used to detect and distinguish minor and major updates to API-protected LLMs. The paper also speculates on the possibility of detecting specific types of updates, such as LoRa updates, by analyzing the changes in model outputs before and after the update. However, further research is needed to confirm this and develop efficient algorithms for such detection. Table 3 provides a summary of the implications of changes in image and logit outputs in API-protected LLMs. It categorizes different scenarios such as no logit change resulting in no image change, logit change without image change, and low-rank image changes. This table is crucial for interpreting various detectable API changes and monitoring unannounced updates in LLM APIs. Figure 5 illustrates the residuals of the least squares solution for an output from a Pythia 70M checkpoint, showing how these residuals indicate whether the output lies within a model's image. The residuals for Pythia 70M decrease as the checkpoints approach the one that generated the output, highlighting the sensitivity of LLM outputs to parameter changes. This method is versatile, as it works with either softmax matrices or direct model outputs, providing a robust way to analyze LLM behavior. Figure 6 illustrates the magnitudes of rows in the softmax matrix derived from the Pythia 70M model. The key observation is that these magnitudes are notably small and exhibit an approximately normal distribution. This distribution is confined within a relatively narrow range, indicating a specific pattern in the model's output layer behavior. This section explores additional applications enabled by access to the LLM's image. Firstly, it discusses the identification of unargmaxable tokens, which are tokens that the model cannot output due to low-rank constraints. This is achieved by utilizing the LLM's image, allowing API customers to discover quirks in the model's behavior. Secondly, it examines the recovery of the softmax matrix from the model's outputs. This involves reconstructing the output layer parameters by hypothesizing that LLM embeddings lie near the surface of a hypersphere. Finally, it proposes improvements to LLM inversion techniques, which aim to recover hidden prompts. By leveraging the LLM's image, the inversion process can be made more efficient and effective. To guard against the identified vulnerabilities, the authors consider 3 proposals. The first is to remove API access to log probes, which is theoretically insufficient as it can still be inefficiently exploited. The second proposal is to remove API access to logit bias, which would be effective but disruptive to clients. The third proposal involves transitioning to alternative LLM architectures that do not suffer from a softmax bottleneck, which is the most expensive but would fully prevent the attack and address other tokenization issues. The potential applications of the methods discussed in this paper can significantly enhance trust between LLM API users and providers without causing harm to the providers. For example, discovering the embedding size of the LLM, which is typically non-public information in proprietary models, does not enable competitors to fully recover the model's parameters or significantly boost their own model's performance. Other critical factors such as training data mix and human feedback remain hidden. Additionally, using model outputs to steal hidden prompts is unlikely to have detrimental effects, as hidden prompt leakage is a known vulnerability. The most significant consequence of these findings might be that model stealing methods that rely on full outputs become cheaper by a factor of V/D, which for GPT 3.5 Turbo amounts to about 25 times. On the other hand, allowing LLM API users to detect model changes can build trust, increase accountability, and promote transparency for LLM providers. The method can implement efficient protocols for model auditing without exposing model parameters or detailed configurations, thereby enhancing model safety and privacy protection for personalized, proprietary models. Therefore, The authors argue that their proposed methods and findings do not necessitate a change in LLM API best practices, but rather expand the tools available to API customers while alerting LLM providers to the information their APIs expose. In this section, the authors discuss a case of simultaneous discovery with Carlini et al., 2024, who proposed a similar approach to understanding API-protected LLMs. The authors highlight an algorithm difference where their V/K algorithm contrasts with Carlini's V/K1 algorithm, noting that while it has little impact on the final result due to numerical instability, it remains an interesting theoretical result. Additionally, Carlini et al. Introduced an improved logprop-free method utilizing parallel queries, which complements the author's OD algorithm, potentially leading to a better combined algorithm for full outputs. The authors also mention their challenges with OpenAI's API, which exhibited stochasticity, prompting the development of a stochastically robust algorithm. In contrast, Carlini et al. Did not report such issues, possibly due to a more stable API endpoint. Lastly, while Carlini et al. Focus on defenses against attacks, the authors concentrate on understanding the capabilities of such attacks, providing complementary insights. In this paper, the authors have demonstrated how the softmax bottleneck imposes low-rank constraints on large language model (LLM) outputs. These constraints can expose non-public information about API-protected LLMs, leading to what is termed a model signature. This signature can be used to reveal model hyperparameters, recover output layer parameters, detect specific model updates, and more. The authors find that current protections against these exposures may be insufficient. More effective measures either eliminate sanctioned API use cases or are costly to implement. They argue that this vulnerability might be more of a feature than a bug, as the benefits for API clients could outweigh any harms to LLM providers. In this section, the authors acknowledge the contributions of Jack Morris and Vitaly Shmatikov. Their insights and feedback were instrumental in the development of this work. Additionally, the section includes references to cited works, supporting literature, and other academic sources that have contributed to the research. Thank you for watching.